Okay, welcome. What a day. It's been a crazy day. I busted out a lecture for you guys this morning. I've got 3 sections of statistics that are working on exams and homework. I got plenty of grading to do, and here I go. I'm going to make this next lecture for you guys. So I want to go into section 6.4, introduce the topic there, which is logarithmic equations. And these equations go pretty smoothly. There's there's not too much weird stuff that happens here, but there's a couple things that we need to keep in mind. So the first thing is that these equations can have what are called extraneous solutions. And I don't know if we've talked about this yet, but an extraneous solution is a solution that the algebra produces that is not a solution to the original equation that we were given and asked to solve. And this can happen in a variety of places. It can happen with rational functions. It can happen with root functions where the index is even. And it can happen in these logarithmic equations. Because all of these functions have something in common, and that is a restricted domain. So we have to be aware that we could come up with extraneous solutions. The best way to deal with this possibility is that all what I call potential solutions must be checked in the original equation. And I'll give that an exclamation point because you gotta keep that in mind. And this is not an optional thing, this is a must. And it's also critical that you check your potential solutions in the original equation. Because as we go through this, we're going to rewrite the equation in a variety of ways, but we have to remember the original equation that we're being asked to solve. The second thing to keep in mind is that the equation needs to be in one of 2 forms. In one of 2 forms. And the first form, and this one's really easy to work with, is we have the logarithm base b of stuff, and I'll call this stuff 1, is equal to the logarithm base b of stuff 2. And there's 2 things here. The first thing is the bases must be the same. We've got logarithm equals logarithm. The bases are the same. And the logical argument here is that in this situation, we can argue that stuff 1 has to be equal to stuff 2. And that is, it's a logical argument, and it allows us to leave the logarithms behind and no longer have to deal with the logarithms. And that's going to result in typically a simpler equation to solve. The other form is that we're going to have the logarithm base b of stuff equals number, some constant. And if the equation is in this form, then we can simply use that idea of switching forms and rewriting it from a logarithmic form into an exponential form. So we'll be able to argue that b, the base here, raised to whatever that number is over here, is going to be equal to stuff. And once again, that's going to allow us to move past the logarithm, leave the logarithm behind, and deal with, hopefully, an equation that is simpler. So please keep those two things in mind. We're going to have to protect ourselves against extraneous solutions, and we're going to have to be working with an equation that is in one of those two forms. So what I want to do is take you through, I think I have about 6 examples that I want to look at to illustrate the issues that we face here. So I'll just do this as a series of examples, and it's simply going to say solve. And I'll do a numbered list here. So the first one, and I've got to check my notes on this because I can't just make these things up. If I try to make these things up on the fly, then it's pretty disastrous. So I've prepared these examples ahead of time. So let's take the logarithm of x plus 2 is equal to the logarithm of 3x minus 1. And this is actually a really basic logarithmic equation. It falls right into that first category where we have, this is logarithm base 10, right? So we've got log equals log, the bases are the same. Here's stuff 1, there's stuff 2. And so the argument here is that stuff 1, x plus 2, has to be equal to stuff 2, which is 3x minus 1. So that allows us, again, to leave the logarithm behind and focus on a much simpler equation. This is a trivial equation for us to solve. So let's subtract 3x. Let's subtract 2. And that will get us to x minus 3x is minus 2x. Gone equals negative 3. So that says x is equal to 3/2. Maybe. Because as I said, these equations can have extraneous solutions. There's no guarantee that that will work in the original equation. So I have to go and run a check on this. And I'm going to check x equals 3/2 in this original equation here. So I need to look at the logarithm base 10 of 3/2 plus 2 and see if that is in fact equal to the logarithm base 10 of 3 times 3/2 subtract 1 and decide whether this is in fact the case. So we can do some fraction arithmetic here. So this will be the logarithm base 10. 3/2 plus 2. 2 is 4/2, so this becomes 7/2. Is this in fact equal to the logarithm base 10? 3 times 3/2 becomes 9/2. 9/2 right here, subtract 2/2 there, is 7/2. And so everything is cool. That checks out. This is, in fact, a legitimate solution to that original equation. So that's basically the process, is that you argue your way out of a logarithm, solve the equation, come up with a potential solution, and then check it back in the original equation. Okay, so let me go on to my second example here. For my second example, let's take the natural logarithm of x minus 2. Let's add to that the natural logarithm of 2x minus 3. And let's have that equal to 2 times the natural log of x. So we have the natural log of x minus 2 plus the natural log of 2x minus 3 is equal to 2 times the natural log of x. And what this looks like to me is I've got logarithm on one side equals logarithm on the other side. The base is the same all the way through, so that's good. What I need to do is combine these two logarithms as a single logarithm because I want log equals log. So these two right here can be combined as a single logarithm using the properties of logs that we talked about a couple lectures back. So we have a log plus a log, the base is the same, and so this can be rewritten using what we call the product rule as the log of this times this. So this will be x minus 2 times 2x minus 3. That condenses this left side to a single logarithm. And then over here, I've got a single logarithm, but I have this multiplier out in front here. And so I've got to deal with that. And we had a property a couple lectures back that says, hey, if you got a multiplier out here, you can drift it up into the exponent position and rewrite this as the natural log of x squared. So that, I've succeeded in getting this into log equals log. The bases are the same, and so I can now argue that stuff 1 is equal to stuff 2. So that lets me leave the logarithms behind and write this as x minus 2 times 2x minus 3 is equal to x squared. And that's really cool because that gets me to a polynomial equation that we're experts at solving. So what I'm going to do is clear some parens over here to write this as 2x squared minus 3x minus 4x is going to be minus 7x. This is going to be a plus 6 is equal to x squared. And this is a degree 2 polynomial equation. I'm going to set that equal to 0, see if I can factor it. If I can't factor it, I'll ship it off to the quadratic formula. But let's subtract x squared from both sides. And that'll get me to x squared minus 7x plus 6 is equal to 0. And that's what I've got to solve. So let me get some space to do some work here. So I'll get this cleared out of here. I want to leave the original equation intact here because I'm going to need to come back to it. So what do we have? We have x squared minus 7x plus 6 is equal to 0. And I believe that this will factor quite nicely as x minus 1 times x minus 6 is equal to 0. Agreed? I agree. And so this will give me two potential solutions. One potential solution is x equals 1. The other potential solution is x equals 6. But again, I don't know whether those will work. It's possible that the algebra is leading me to extraneous solutions. So let's check these individually. So here's my first check. So let's check x equals 1. And here's the original equation right here. And so I've got to plug that value of x back into this guy. So I'm going to get the natural log of 1 subtract 2 plus the natural log of 2 times 1 subtract 3. And I'm asking whether this is in fact equal to 2 times the natural log of 1. Did I do this right? Yeah. So I'm putting in a 1 for each value of x. I did it correctly. But watch what happens right here is this becomes the natural log of negative 1. And I'm going to stop right there. Because the natural log of negative 1 is something that we're not going to deal with. And so I'm just going to say, hey, stop. You don't need to go any further. Because for our logarithms, negative 1 is not in the domain. Remember, logarithms, we're sticking with input that is strictly greater than 0, that's positive. Now, if you want to go and look at logarithms of negative numbers, this is a beauty right here. What it's going to do, it's going to take you into the world of complex numbers and the topic of complex analysis. And this guy right here is sweet. I'm not going to go there. So I'm going to stop there and I'm going to say, no, x equals 1 is not a legitimate solution. It's an extraneous solution to this equation. So let's go check the other one. The other one is x equals 6. And if I plug that into this original equation, I have the natural log of 6 minus 2 plus the natural log of 2 times 6 minus 3. And my question is this in fact equal to 2 times the natural log of 6? So let's figure out what we've got here. This is going to be the natural log of 4 plus the natural log of 12 minus 3 is 9, agreed. And the question is that in fact equal to 2 times the natural log of 6? So let's clean this up some. Natural log of 4 is a perfectly legitimate number. Natural log of 9 is a perfectly legitimate number. Both 4 and 9 are in the domain of the natural log function, so I can clean this up and write it as 4 times 9, bring those two logs together as a product. Natural log of 6 is a perfectly good value. 6 is in the domain of the natural log function, so I can write this as the natural log of 6 squared. I can drift that exponent, this value of 2 up into the exponent position. So this gives me the natural log of 4 times 9 is 36. Is that equal to the natural log of 6 squared, which is 36, and everything's cool. So this original equation has one and only one solution, and it's that guy right there at x equals 6. X equals 1 is an extraneous solution. Okay, so let me clear out some space here, go on to my next example. Let's see. So where are we in this list? Let's go to number 3, I believe, in this list. And number 3, let me grab a little sip of water here. Number 3, let's take a look at this equation and let's solve logarithm base 2 of 5 minus 3x is equal to 3. So that's fairly straightforward. It fits into that second category that we said where we have logarithm of stuff equals number. And what I can do is I can simply rewrite this from logarithmic form into exponential form. And again, that will allow me to leave the logarithm behind and hopefully result in an equation that is simpler. So this will become this base 2 raised to this power 3 will give us this stuff in here. Okay, now this is going to be a really simple equation to solve. 2 to the third is 8 is equal to 5 minus 3x. Let's subtract 5 from both sides. That'll give me 3. Subtract 5, that'll give me 3 is equal to negative 3x. And this is going to give me, when I divide by negative 3, x is equal to negative 1. Maybe. It's possible that that's an extraneous solution. If that's our only potential solution and it comes out to be extraneous, then I will conclude that this equation has no solution. I don't know, let's check it. So if I go back to this original equation and put in a negative 1, I got logarithm base 2 of 5 minus 3 times negative 1. And the question is this equal to 3? So 5, this becomes a plus 3. This becomes a logarithm base 2 of 5 plus 3 is 8. And is that in fact equal to 3? And the answer is yeah, it's perfectly good. So that means that this x equals negative 1 is a viable solution. It's a legitimate solution. Now, if this check, as I said, if this check didn't work out, then we would conclude that this equation has no solution. All right, here we go. Let's go into this next one. So this next one, let's take 2 times the logarithm base 3 of x minus 2 is equal to 2. So 2 times the log base 3 of x minus 2 is equal to 2. And again, this is looking like that second form that I put up there where we have log of stuff equals number, but we've got this guy out in front here, and I'm going to start by drifting that up into the exponent position. So to get this equation in precisely the form that we need, I'm going to write this as the logarithm base 3 of x minus 2 squared is equal to 2. So again, drift this up into the exponent position. And now I can take this form of the equation, rewrite it in an exponential form, leave the logarithm behind, and I'll have 3 raised to the second power is equal to x minus 2 squared. Right? So this base raised to this power will give me this stuff in here. So 3 to the second power is equal to that. Now, let's clean this up. So, but take a look, right? This is going to be a very simple equation for us to solve. We're experts with equations like this. 3 squared is 9. X minus 2 times x minus 2 is x squared minus 4x plus 4. So I'm being presented with a degree 2 polynomial equation. I'm going to set this equal to 0 and see what I can do from there. So if I subtract 9 from both sides, I will get to x squared minus 4x minus 5 is equal to 0. So there's a quadratic equation. This one's going to factor. If it didn't factor, I would take it to the quadratic formula. Okay, so let's factor this. And this is going to factor, let's see how, as x plus 1 times x minus 5, I think. Let's check that. So that's good, that's good, that's good, that's good. Yes. So that factoring is correct. So our potential solutions here are x is equal to negative 1 or x is equal to 5. But again, I always put a question mark there to remind myself that I don't really know whether those are the solutions or not. And I've got to go and check those back in the original equation. So here's our original equation right here. And I'm going to go and plug each of those in and see what happens. So let's check x equals negative 1. I'm going to grab a fresh pen here. This one seems to be dimming a bit. So we got that. So if we check x equals negative 1 back in this original equation, we've got 2 times the logarithm base 3 of negative 1 minus 2. And I'm asking, is this in fact equal to 2? And the answer is no. Because what's going to happen right here is that guy's going to go negative. And so this will become 2 times the logarithm base 3 of negative 3. And I'm just going to stop right there. Because in this course, we're not dealing with logarithms of negative numbers. So what that means is that x equals 1 is not a solution. It's extraneous for us. Let's check the other value. The other potential solution is x is equal to 5. So if I go back to this original equation, then I have 2 times the logarithm base 3 of 5 minus 2. And I'm asking, is this in fact equal to 2? Okay, 5 minus 2 is 3. So this will take us to 2 times the logarithm base 3 of 5 minus 2 is 3. Is this equal to 2? Well, take a look. What's the logarithm base 3 of 3? Dude, that's 1. So 2 times 1 is equal to 2. This checks. So where are we? So x equals 5 is a legitimate solution. X equals negative 1 is extraneous. Nice. Whew. Okay, so I've got 2 more examples that I want to bust out here. And again, you know, I'm covering a lot of territory here, but, you know, if I erase something too soon, you can always pause the video, go back and check what was on the board before. Oh, and here's another cool thing. Our videos are closed captioned. Oh, who knew? I didn't know. All right. right, so let's see, what do we have here? We're at number 5 now, I think. So my next example is going to look like the logarithm base 2 of x, add to that the logarithm base 2 of 5 is equal to 2. So log base 2 of x plus log base 2 of 5 is equal to 2. So this one's going to be pretty straightforward, I think. Because what we've got, we're heading towards log equals number. But I need to combine these two into a signal logarithm. But we know from our properties that if we have log plus log and the base is the same, I can write this as the logarithm base 2 of x times 5. The product of those two is equal to 2. So what this becomes is the logarithm base 2 of 5x is equal to 2. Perfect. So now I've got log equals number, and so I can rewrite this, leave the logarithm behind, and say if you have 2 raised to the 2 power, so this base raised to this exponent will give you that guy right there. So this says 4 is equal to 5x. So that simply says your potential solution is x is equal to 4/5, maybe. All right, so let's check this back in the original equation. So if I come back here and I check this, I have the logarithm base 2 of x, which is 4/5, plus the logarithm base 2 of 5, and I'm asking the question, is that in fact equal to 2? So start by making sure that the logarithms are legitimate. Log base 2 of 4/5, 4/5 is greater than 0, everything's cool here. That will be some number. Logarithm base 2 of 5, 5 is greater than 0, this is legitimate, this will be some number. And so I can actually multiply these two guys together, and this will become the logarithm base 2 of 4/5 times 5, and I'm asking, is this equal to 2? So look what happens here is we have a division by 5, we've got a multiplication by 5, they're gone, and so this simplifies to the logarithm base 2 of 4. Is this equal to 2? You bet. Because this is the exponent that goes on 2 to get you 4, and that's 2. This checks out. So where are we? This is a perfectly legitimate solution to that equation. This pen is kind of dimming also. And at some point I'll tell you my story about these pens and, you know, them running out and recycling them and stuff like that. I got a whole story there, but, you know, I won't go into it right now. Whew, okay, so there's that example. I got one more, so bear with me. I got one more. This is number 6 in this list. And what's this one going to look like? So let's take the let's take logarithm base 10 of x plus 4. Let's subtract from that the logarithm base 10 of x, and I want that to be equal to the logarithm base 10 of x plus 1. So let me double check that. So we've got log of x plus 4 minus log of x is equal to the log of x plus 1. Okay, so here we go. This is starting to look, to me anyway, this is starting to look like I should be headed towards log equals log. The base is the same for all of these logarithms, and that's going to be the case for us. So what I need is a way to combine this left-hand side into a single logarithm. So from our properties, we know that if you have log minus log, and the base is the same, you can rewrite this as the logarithm base 10 of x plus 4 divided by x. So it's this guy divided by that guy. This is what's called the quotient rule. And over here we have the logarithm base 10 of x plus 1. So we're in that first scenario where we've got log equals log, bases are the same. The argument here to leave the logarithms behind is that x plus 4 over x would have to be equal to x plus 1. So again, that results in a simpler equation, and I can now tackle that with the tools that we have from algebra. And I think I said this in the last lecture, is don't forget about algebra. We're doing different kind of stuff here, but algebra still exists for us, and algebra is still our friend. So what I'm going to do to tackle this is I'm going to start by getting rid of that fraction structure, and I'm going to multiply both sides of this equation by x. So when I do that, I'll have x plus 4 is equal to x times x plus 1. That's a simpler equation because it no longer has the fraction structure in it. I'm going to clear some parens here and say we've got x plus 4 is equal to x squared plus x. Once again, I'm faced with a degree 2 polynomial equation. I'm thinking set this thing equal to 0 and see what happens. So if I subtract x, if I subtract 4, then I get to 0 is equal to x squared subtract 4. Check me on that. Did I do this correctly? X's are gone, 4's are gone. Yeah, this is good. So what's going to happen here is this is a really simple equation for us at this point in time. We know that we have x equals plus minus 2. But again, please don't make the rookie mistake here of looking at that and saying, oh, x equals 2. This is a degree 2 equation. It's got 2 solutions. And here they are. Maybe. Now, these are guaranteed solutions to this. But what about this original equation up here? This is where we have to check those 2 potential solutions. All right, so here we go. So let's check x equals 2. You plug in x equals 2, you've got the logarithm of 2 plus 4 is going to be 6 minus the logarithm of 2. And the question is this equal to the logarithm of 2 plus 1, which is 3? Okay, the first thing is all of these logarithms pose no problem, right? 6, 2, 3, they're all in the domain of the common log. So that means that I can combine these and say this is the log of 6 divided by 2. And I'm asking, is that equal to the log of 3? And it should be pretty clear that 6 divided by 2 is 3. So this is log of 3 equals log of 3. So that checks out. No problem. So x equals 2, is a good solution. Now, does that imply that x equals negative 2 is not a solution? No, it does not. We've got to go and check it. So let's do that check. And let's check x is equal to negative 2. When I do this, up here in this original equation, I have the log of negative 2 plus 4 is 2 subtract the log of negative 2. Dude, and I'm going to stop right there. Because the log of negative 2 is not in the domain for our common log function. So I'm not going to go any further. I'm just going to say stop. This guy is extraneous. The only solution to this equation is x equals 2. Whew. Okay. Now, the last thing that I want to show you is we haven't done a whole lot of graphing of exponential or logarithmic functions. We've talked about the basic shapes, domain and range and things like that, but I want to go and take a closer look at that and bring out this next example. So I'm done with our numbered list of examples of log equations. And I want to go and shift gears here a little bit and switch to a different example. And I want to talk about graphing. So let's graph a log function. And let's take f of x is equal to the logarithm base 2 of x plus 4. And then we will add 2 to that. Now the first thing that I'd like to do here is come up with at least a primitive sketch of what this is going to look like. So let me see what I can do here. So we've got f of x here. And this, I'm going to see this as a modification of the log base 2 graph. And I think we saw that some lectures back. But this is going to take the basic, the log base 2 graph, and it's going to shift it 4 units to the left and up 2 units. So the log base 2 graph is sitting in here like this. I'll do it in a dashed format. And we know that it's a strictly increasing function. It has an x-intercept right there at 1, 0, at 1, 0. We know that it is asymptotic to the negative y-axis, and it's going up from there. So what's going to happen is when I shift this 4 units left and up 2 units, this vertical asymptote here at the y-axis is now going to come over here to the point x equals to the line x equals negative 4. And this x-intercept or root right here is going to go 4 units left and up 2 units. So it's going to be up here somewhere. And so this graph, this basic shape right here, is going to go zoop, zoop, and it's going to be up here something like that. Lousy drawing here, but it's going to look something like that. And that suggests to me that we have a root there and we have a y-intercept there. So in a moment I'll go and find those. But the first thing I want to do here is to just make some basic statements about domain and range. Is this thing one-to-one? So here's the domain. The domain is fairly straightforward. It's defined by this vertical asymptote here. And so we're talking about values of x that are strictly greater than negative 4. And the range here is fairly straightforward. This guy is going to go down to negative infinity, is going to go up to positive infinity because it's increasing throughout its domain. And so I'm going to argue that the range for this function is all reals. The next question is this thing one-to-one? Well, it's certainly a function. It passes the vertical line test, but it also passes the horizontal line test. So the answer is yes. And this is really cool, because you know what? If this function is one-to-one, it's got an inverse, and I do want to go and find the inverse. But first, I'm intrigued about finding these 2 points right here, this root and that y-intercept. So let's come over here and do that work to find those. So where's the root here? So the root is going to happen when the function is equal to 0. So that's going to give us this equation, logarithm base 2 of x plus 4 plus 2 is equal to 0. Now we just talked about how to solve logarithmic equations, and that's what we've got to do here. So this is going to turn into, I'm going to first isolate this logarithm, and I'll have logarithm base 2 of x plus 4 is equal to negative 2, right, by subtracting 2 from both sides. So that move gets this into logarithm equals number. And now I can leave the logarithm behind by arguing that if I take this base 2 and I raise it to this exponent negative 2, I'll get stuff. That stuff right there, x plus 4. This is a very simple equation to solve. 2 to the negative 2, that's 1/4, is equal to x plus 4. Subtract 4. Do the fraction arithmetic. 1/4 subtract 16/4 is equal to negative 15/4. So that says that our root is at negative 15/4, 0. Which, based on my graph, is legitimate, because I know that this root's going to be pretty close to that vertical asymptote at x equals negative 4. And 15/2 is negative 3.75. So I'm satisfied with that. It looks okay to me. So there's the root. Now, let's go and find the y-intercept. Because that's this guy up here. Now this is easy. This is when x is equal to 0. So the function evaluated at 0 is going to be the logarithm base 2 of 0 plus 4 is 4 plus 2. This logarithm is quite simple. We can do this one in our heads. Logarithm base 2 of 4 is the exponent that goes on 2 to get you 4. That's 2 plus 2 is equal to 4. As they taught you, 2 plus 2 equals 4. So that says that our y-intercept is at 0, 4. Which again looks reasonable based on my crappy drawing here of this function. All right, now here comes the really cool part. Is I want to go and find the inverse function for this. Because we established that this function is one-to-one. It's got an inverse. I'm going to go find it. So let me clear this out. I want you to hang on to these two ordered pairs, the root and the y-intercept, because maybe you can see this coming. But when I go to f inverse, I'm going to come up with a function where the root and the y-intercept are going to swap positions. This y-intercept is going to become an x-intercept for f inverse, and this x-intercept here is going to become a y-intercept for f inverse. Watch for that. Let me get some space to work here. All right, here we go. All right. All right, so let's go and find f inverse. Oh, my heater just kicked on. Must be late in the day. I know what that means. I need to wrap up this lecture. Okay, so to find f inverse, I'm going to go through that process that we've been using for a while. Let's start by ditching the function notation. We've got y is equal to the logarithm base 2 of x plus 4 add 2. And the first step in this process is to swap x and y. So this is going to look like x is equal to the logarithm base 2 of y plus 4 add 2. And now I have the task of solving this equation for that guy right there. Okay, so here we go. We're solving a log equation here. We just talked about how to do this. So I'm going to subtract 2. So that'll give me x minus 2 is equal to the log base 2 of y plus 4. And this is in that form where I have logarithm equals stuff or numbers, And so I can rewrite this and say if you take this base 2, you raise it to that guy right there, you'll get this stuff, y plus 4. So what that says to me, subtracting 4 from both sides, is we've got y is equal to 2 raised to the x minus 2 power, subtract 4. So now we go to the function notation, and so I'm going to argue that f inverse of x is equal to 2 to the x minus 2 subtract 4. That's my claim. Now I can prove that by going and doing the function composition in both orders. I'm not going to do that here. It might also be nice to graph this on the same set of axes as f of x and make sure that we see that reflection across the line y equals x. I'm not going to do that. But what I am going to do is come over here and talk about domain and range. So for this function f inverse, what's the domain? It's an exponential function. So the domain is all reals. And what about the range? Remember, for an exponential function, and this is base 2, it's an increasing exponential function. The range is determined by the horizontal asymptote. And when I take this 2 to the x graph and I subtract 4 from it, that drops that 4 units. And so that horizontal asymptote is now at y equals negative 4 instead of the x-axis. So I'm looking at values of y that are strictly greater than negative 4. Now, are you ready for the really cool part? Ta-da! Take a look over here at the domain and range for f of x and compare that with the domain and range for f inverse. They have swapped. I'm rock solid with this. It looks good. Sweet. That's nice. It feels good. Okay, now here's the other thing, is that this is going to wrap up chapter 6. And this will let us move forward to our upcoming exam I've uploaded some videos. I found a really great video for this topic of solving logarithmic equations. I've put that up, and so work through that. I have a new quiz up on our Canvas page, and I'll see you soon.